You know the feeling. You're staring at a loading screen, waiting for concert tickets to drop, or trying to check out during an online sale. The clock strikes, thousands of people hit refresh at the exact same second, and the entire website simply freezes. But this extends far beyond entertainment. When digital payment gateways stall, or when a rideshare driver is stranded on the street because their app won't connect, that loading screen translates into real-world panic and lost income. When these platforms collapse, people usually blame the servers. They picture a massive data center somewhere catching fire. But the hardware is rarely the culprit. The system is almost always failing because of an invisible flaw in the software's mathematical design. Separating amateur code from resilient enterprise infrastructure comes down to two specific concepts: abstract data types, or ADTs, and Big O notation. In massive digital ecosystems handling millions of requests a minute, writing code that simply works is not enough. Algorithmic efficiency is the absolute baseline for a company's survival. Think about the last time you bought something on your phone. You tap a button and the item goes into your shopping cart. You don't know or care how the database handles that request. That clean, isolated experience is governed by an abstract data type. An ADT is strictly a behavioral contract. It defines exactly what a system is allowed to do, like adding or removing an item, completely separate from the technical implementation of how that data is physically stored in the backend. Take a stack ADT. Its contract allows two things: push an item onto the pile or pop it off. Because this interface is locked, engineers can build the underlying mechanics using a rigid array or a scattered linked list. The user experience remains identical. By hiding the mechanical details, ADTs allow software architects to design massive, complex systems based purely on expected behaviors. They don't get paralyzed trying to figure out the plumbing before they've drawn the blueprints. This chart displays Big O notation, a mathematical framework used to evaluate how algorithms perform. Notice that the vertical axis isn't an absolute measure of seconds on a stopwatch. Big O is a predictive metric. It measures how processing demand grows as the size of the dataset expands. Look at the flat green line at the bottom. This represents O of 1, or constant time. Retrieving a specific data point from a well-designed system takes the exact same computational effort whether the database holds 10 items or 10 million. Slightly above that is logarithmic time, written as O of log n. Algorithms like binary search use this approach. It's a method that finds an item by continually splitting a sorted list in half. That mathematical halving is exactly what allows search engines to instantly pluck your specific query out of massive global databases. Returning to the chart, we see the straight blue line ascending steadily. This is O of n, or linear time. It represents a strict one-to-one relationship. 10 items require 10 steps of processing, and 1 million items require 1 million steps. Understanding these basic mathematical growth curves is the first necessary step to predicting exactly when an application will bottleneck under pressure. This chart highlights the red curve violently skyrocketing off the axis. This is O of n squared, or quadratic time. When you write algorithms that perform actions like nested loops, operations multiply exponentially against the input size. This code snippet demonstrates the threat. The nested 4i and 4j loops mean the program checks every single item against every other item. Processing 10,000 users this way requires 100 million operations, which will instantly melt a server. Think about the financial stakes for a platform matching user preferences for recommendations. Calculating viewer similarities using an O of n squared algorithm across hundreds of millions of accounts would take days to train and completely bankrupt their cloud computing budget. This graph compares multiple time complexities side by side. You can clearly see the exact divergence point where the upper curves, like n squared and n factorial, violently separate from the sustainable lower curves. That gap represents the difference between a functional tool and a system-crashing liability. At the scale of millions of active users, an O of n squared algorithm is a guaranteed systemic failure waiting to happen. So put yourself in the role of a chief technology officer. You are tasked with designing a new feature to find a single username inside a database of 5 million active users. You have 3 architectural choices. Option A is a sequential search through a standard array, checking every name one by one. Option B is a binary search through sorted data. Or Option C, utilizing a hash table, a data structure that uses mathematical functions to map keys directly to values for instant retrieval. The path you choose determines if your application feels instant or unresponsive. These optimizations move past theoretical math. They directly protect the time and livelihoods of the 5 million people relying on your platform. Abstract data types provide the behavioral contract for the user, ensuring the interface remains reliable and clean. Big O notation provides the mathematical map to ensure that backend architecture can sustain the weight of its own growth. Any programmer can write code that executes on their own laptop, but a professional analyzes complexity to build infrastructure that endures.